Welcome back to Physics in Minutes. Today, we're dealing with 2D kinematic physics problems using the kinematic equations that we saw last time. If you haven't seen my video about 1D kinematic equations, I suggest you check it out first and then come back here. So let me give you an example that stumped me back when I first started doing problems like this. Let's say we have a table, and the table is 1 meter tall. On the table, there is a cup that for some reason you decide to smack off the table at 5 meters per second in the x direction, and it falls off the table. It's obviously going to fall in some form of an arc because it already has some velocity. The question is, how far from the table is the cup when it hits the ground? Now, you could look at the kinematic equations and try and pick one, but again, if you're dealing with 2 dimensions, as we clearly are here, you can't do it with just one equation. The first step is breaking it up into x and y components and then going from there. More often than not, the way that you connect those 2 equations back together is by finding time. And that's what we're going to do first. Because if we know how long it takes the cup to move from this point to that point, we'll be able to find out how far it's gone. So to find time, the only thing that really matters is how long it's taken to fall. So if we look at the y direction first, the y direction doesn't care at all how much the cup moves to the left and right, because that is only the x direction. The y direction only cares about movement up and down. In this case, the cup is falling 1 meter. So we have the height difference. All we need to do is find time. So as I explained last video, in order to do this, the best way is you write down what you have on one side, what you need on the other side. So right now we're dealing specifically with the y direction. What we need is time, because then we can use that to find out how far the cup has gone in the x direction. What we have is the height, which is 1 meter. I explained this last time, but in case you don't remember, height is just the difference between your final position and your initial position. So in this case, the initial position is up here, the final position is down here. What that means is that height is negative 1 meter, because the cup fell 1 meter below where it was. We also have acceleration, because that is just negative 9.8, which is just negative g. We have as well the initial velocity in the y direction. Because the cup was only hit with a velocity in the x, the y velocity has to be 0. So now that we have those things, we bring up the equations, and once again, we're just going to look for the equation that has everything we have, everything we need, but nothing else. As an example, this equation right here, it looks somewhat good, but it has this pesky final velocity there, which we don't know. So we're not going to use that. Instead, we're going to use this equation here, because that has everything that we need. Let's use this equation and let's start solving for it. Let's start by just writing it. X equals x naught plus v naught t plus 1/2 at squared. And we've already mentioned a few things here. One is that the initial velocity right here, that's 0. Again, because you hit the cup horizontally, not vertically. So the initial velocity is 0. We also have, if you move this x to the other side, this x naught, by subtracting it, you have x minus x naught, and that is equal to, we already found, minus 1. So minus 1 must equal 1/2 a, which we said was minus 9.8 just because it's gravity, and t, which we don't know, with a squared on it. At this point, let's just solve algebraically. If we multiply by 2 on both sides, we get minus 2 equals minus 9.8 t squared. Let's divide by 9.8, and they're both negative, so the negatives goes away. We have 2 divided by 9.8 equals t squared, but we square root everything, which ends up being 0.45 seconds. So again, to emphasize what we did, we started with the y direction because the time it takes for the cup to move is entirely dependent on how long it takes to hit the ground. Once it hits the ground, it's completely stopped. So if you can find out how long that takes, then you know the time. Now that we have time, we can then go back to the x direction and simply find out how far the cup has traveled in the x direction when it was falling down in the y direction. So we have t is 0.45 seconds. We have to remember that. And now let's look at the x. Now back in the x direction, again, we ignore the fact that the cup fell because we already took care of that in the y direction. And we got that time was 0.45 seconds. That's all we needed with the y. Now the y is done. We look at the x specifically. The cup has moved some distance here. We'll just call it d. What is d? Now I don't have it written on this slide, but we already saw that earlier the velocity in the x direction was 5 meters per second. So let's write out what we have and then what we need. Doing it a little bit smaller so we have some space over here. We have time because we just found that out. We have initial velocity because we know what that is. We need distance. There is one more thing that we have that I haven't pointed out, and that is acceleration. When something is in free fall, like this cup, there is only one possible value of acceleration in the x direction. It has to be 0. And this just makes sense. Consider stepping off a table or jumping off a cliff or whatever. As soon as you jump, you have lost all of your acceleration in the x direction. Gravity isn't moving you forward or back, it's only moving you down, which means there's no acceleration whatsoever in the x direction. And this is a concept that a lot of people don't quite get when it comes to physics, but it's really, really important. When you're doing two-dimensional problems, if it's free fall or if it's something like this, the acceleration in the x direction is always, always going to be 0, which means that we are always given the acceleration in the x direction, unless it specifically says that there is something else. With all of that, we now look at our problems. And it's actually fairly simple. There are a couple of different ways that we could do this. You could use either this problem here, or we could once again use this problem. Both of those would get you to the same answer. The only thing you'd have to realize if you use the first problem here is that your initial velocity is going to be equal to your final velocity. Now, how can I say that? Simple, because acceleration is 0. If there is no acceleration in the x direction, then the initial velocity in the x has to be the final velocity in the x, which is another thing that people don't entirely understand. So let's go with the first problem first. What I'm trying to find is d. We already know that d is going to be x minus x naught. So in both cases, I'm just going to solve directly for that. So I'll have, starting off, if I move the x naught over, d is 1/2 v naught plus v times time, which I ran out of space, but it's right there. As I said, if there's no acceleration, v naught is equal to v, which means v naught plus v is going to be 10 because they're both 5. d is equal to 1/2 times 10 times 4.5, which ends up giving me 5 times 4.5, or 2.25 meters. So right here is our answer. And we arrived at that because, again, if acceleration is 0, then the initial and the final velocities are identical. Now, what would happen if instead of using this equation, we use this one? Because I said both of them work. Let's go through really quickly and show it's the exact same thing. Once again, we're just going to solve for d, move the x naught to the other side and subtract it, and that's d, is equal to v naught x times t plus 1/2 at squared. So d is going to equal 5 times 0.45, which is just 2.25 as we already saw, plus 1/2 at squared. And at this point you may be concerned because you have to square the time, which is 0.45, and that might get messy, but remember, what's the acceleration in the x direction? It's 0. There's nothing else to it. So that entire term goes away, meaning that d is 2.25 plus 0, or just 2.25, which is the exact same thing that we got earlier. And these are both in meters. So that is an example of a 2D kinematic physics problem that stumped me back when I was first doing it. If you have any comments or questions or concerns, go ahead and let me know down in the comment section below. One last thing before you go that I want to emphasize: when you're dealing in 2 dimensions, the first thing you have to do is break it up. Look at the x and the y separately. They will connect generally through the time component. So once you've found time from the y direction, you can then input it into the x direction or vice versa. All that being said, these aren't much more difficult than 1-dimension problems. If you can do it in 1D, you can do it in 2D, it just takes a bit more time. And that's it for this video. Thanks for watching, and I hope you'll be here next time for the next one.